Mul on au avada kaitsmiskomisjoni istung, mille aluseks on infotehnoloogia teaduskonna dekaani korraldus 27. augustist 2013, kus on siis kõige muu kõrval öeldud, et moodustan Ivo Müürsepp'a doktoritöö Robustsed detektorid kognitiivsele raadiole kaitsmiskomisjoni ja määran oponendid all järgnevalt. Esimees Vello Kukk, kes nüüd sõnu siin räägib, liikmed Leo Mõttus, Automaatika Instituudi professor kohal, Jüri Vain, Arvutiteaduse Instituudi professor, samuti kohal, Ole Märtens, Johan Seebecki Elektroonika Instituudi juhtivteadur, Rein Haavel, küberneetika seiresüsteemide osakonna juhataja ja ühtlasi ka oponendid Tommy Svensson, former vice president Ericsson AB, öelda Rootsi, Peep Miidla Tartu Ülikoolist, Matemaatika Instituut ja Andres Reial, master researcher Ericsson Lund, Rootsi. Nii, kuna dokumendid on kõik korras, siis ma annaks järgmiseks sõna töö juhendajale ja ühtlasi will switch over to English to make everything what happens here understandable to all participants, and supervisor will have. Maybe you have to go here
So
also.
thank you very much. I guess I need to characterize Ivo in some sense. And the most important thing with Ivo is that he's actually a rather talented guy. I sort of like him often. But the trouble with him is that he does too many things, you know. He is PhD student in our institute. He's assistant, teaching assistant in our institute, full-time teaching assistant. Beside of that, he is lieutenant of the voluntary defense organization of Estonia, kaitsmine. And then he participates in the work of corporation Sakala, the student organization. He runs in the woods during orientation, and the most importantly, he sits half of the days in Facebook. I think he spends most of his time on Facebook, actually. I'm his friend, that's why I know. But beside of that, he's a talented guy, and all those other things have taken a lot of his time, so he has been forced to postpone the defense several times. It has taken longer time than it should have been. But as said, he's a good guy. And that's what I wanted to say. So thank you.
Thank you very much. And now it's your turn to make your presentation, please.
Thank you. Can everybody hear me? Even in the back row? Okay. Welcome, dear opponents and honorable members of committee, all my colleagues and students and friends and all other ladies and gentlemen. I'm going to present you my work in following 25 minutes. And the topic of the thesis is to develop robust detectors for cognitive radio. At first, we start with some background information about why we are doing this job, and then I'm briefly presenting you what have been done and what kind of results we have obtained. So I start with this little foggy picture. Probably everybody has something like that with them. Everybody nowadays using mobile internet, and the number of users is growing every day, and also the users want more and more bandwidth, more and more higher data rates. This means for a physical world that we need more and more frequencies out of electromagnetic spectrum, which are presented here as a rainbow. Rainbow is a really good example. It's just a part of electromagnetic spectrum. I can say that the rainbow has much more colors, but we don't see them. So anyway, at first it seems that if we need more bandwidth, we just use more colors of the rainbow and problem is solved. But there actually is a problem that we can't use most of these available frequencies because as everybody wants to transmit on some frequencies, all frequencies are divided between users based on license. So you can go and buy yourself some kind of frequency and nobody else is allowed to use it. And actually the problem is bigger here because studies have shown that about 15 to 85% of the times actually these licensed frequencies are not used. It means somebody owns the yellow color, but it uses it only a little bit of time. Rest of the time this color is theoretically available, but you can't have it because it's licensed. It belongs to some user and other users are not allowed there. So the solution to this problem was proposed about 15 years ago by Joseph Mitola. And the idea was that your cell phone needs a small artificial intelligence inside of it, and it's called a cognitive radio. It means this kind of radio device that is available of his surroundings. And in the simplest case, it's called a spectrum sensing cognitive radio. It means that your device is listening all these spectrum bandwidths that are given to some other so-called primary user, and if it detects that the primary user actually doesn't use his bandwidth, then this cognitive radio is smart enough and it will start to use this temporarily available channel for its own purposes. But as the moment as it hears that this proper owner is coming back online, then this cognitive radio notices this, ends its transmission on this channel, finds another one which is currently unoccupied and starts to use this one. So it listens. If the primary user is silent, nothing comes from this TV tower, then it can use those free available channels for own communication. But as long as it hears that primary user is back online, then you have to change the channel. This is the basic idea of spectrum sensitive cognitive radio. And of course there has been lots of research and work done by this sensing algorithm, detection algorithm, how to make this artificial intelligence to work as well as possible, to be very sensitive to hear the smallest amount of power from primary user. But most of these algorithms are based on assumption that this background noise is Gaussian, only this thermal noise. But again, studies have shown that on these urban areas there's a lots of interference. For example, household devices, electric transportation, and so on and so on. And they are causing noise called impulsive noise, impulsive interference. So in real life it means that if your neighbor is shaving on the morning, then your internet connection goes away, in the worst case. And that's why in this thesis we have studied how to make those sensing devices or detectors as sensitive for, in one hand, to be sensitive for primary user signals, and the other hand to be insensitive for impulsive noise. This is the basic idea what we have trying to do here. So task statement was simple to work out three types of robust detectors. Robust means that this detector is sensitive to signal, but it doesn't let to be disturbed if the background noise is not Gaussian anymore, but it also has strong impulsive component. And why this exactly three detectors, not more or not less? Because this energy detector, cyclostationary feature detector, and matched filter detector are the three classical most used detectors. So we want to build this analog for each of one of them. And why there is different types of detector, which one to use depends on how much a priori information we have about this primary user signal. The energy detector is best when we have absolutely practically no information about which kind of signal is sent by primary user, and the matched filter detector demands almost to know everything about this primary signal in order to discover it. And in other hand, more and more we know about signal, we will get the more and better and sensitive algorithms. So this leads to less information, but it's also less sensitive, matched filter needs the most information about primary signal, but it's also the most sensitive one. So we worked out the 3 types. If some future developer wants to build a cognitive radio, then according how much information he or she has about this primary signal, he or she can choose one of those 3 detectors. And these additional conditions are stating the robustness. It means that our detectors should work almost as good as the regular energy detectors when there is no impulsive noise. And when the impulsive noise is present, they should still continue work almost as well. The structure of the work that have been done is divided into these 6 parts or 6 points. First, we started to a little study of these existing detectors, and we also studied how impulsive noise affects them. Then another important part was the derivation of our model of impulsive noise, actually joint noise of impulsive and Gaussian. Then for our detector we need some estimations for some values of noise. So we worked out the maximum likelihood estimators for these important parameters of our noise. And of course the main part was then based on this information we had to work out these 3 robust detectors. And also, as you can see, we have to estimate some parameters, and then we did a little study how this uncertainty of estimation of those parameters affects the work of our detectors. There is a little picture to show what we mean about impulsive noise. This main part of this picture is occupied by Gaussian noise, and impulsive noise is such kind of noise which value is much larger than we could expect from this Gaussian distribution. And usually we also assume that those noise impulses are not happening very often. So to model our noise impulses, or this probability distribution function of noise, we took this kind of model that we assumed that most of the time there is no impulses. This is represented by this delta pulse here. And then there is a small probability called C that says that there is noise impulse which amplitude is distributed uniformly. We took this uniform distribution because this maximum entropy assumption, we worked out the detector for the first case when we have absolutely no information how this impulsive noise is actually generated. And when we have some better model, then we can make our detectors probably even better, but we can show that it works even on this worst case scenario. And those limits, b and minus b, they are caused by receiver. For example, they can be the maximum and the minimum values of the analog to digital converter output. It means that our numbers that we are dealing in those algorithms can't be larger than b or smaller than minus b. They are probably limited. As in some parts of the work we needed to look at this model in actually in n dimensions, then we have to work out for this probability distribution function for the higher dimensions. Here is example of the 2-dimensional impulsive noise. On this picture you can see that again there is really probable that when we have 2-dimensional vector, then both of those values having 0 value, they don't have impulse. This is the highest probability. That's why we have this delta peak here. There is a bit higher probability that one or the another part of the vector is corrupted by impulsive noise. This is represented by those walls. And there is really small probability that both of the vector's elements are corrupted by impulsive noise. And this is represented by this large plane, which actually are really small. Here we use the large values of C to just show on the picture. In real time, this plane is really large and really small height. I'm not going to tell you about Gaussian distribution. I assume that most of you are well aware of this. But we assume that there is at the input of our receiver both, of course, thermal and Gaussian noise, and then also this additional impulsive noise. So when we want to calculate this joint probability distribution function of them both noises, then it's mathematically straightforward. We just have to calculate the convolution between those two separate probability distribution functions. And here is this result for the one-dimensional joint noise. And we can see that it resembles Gaussian noise, but it has those much longer tails. As we wanted to model the impulsive noise, then we need the longer tails for probability distribution function. And again, everything that wants to cross the P can do it in real receiver, so it's concentrated into those small delta impulses. Again, the values of variables are here chosen so that we can see the details of this probability distribution function in real life scenarios. These areas are actually also really, really slow and small, and also those delta pulses. And this convolution is mathematically, it's simple to understand that we need to take convolution, but these actual results are really not user-friendly, so we have to make some approximations about how our noise looks. And then with this dashed line, you can see this exact probability distribution function from the last picture, and the red line, red thick line, represents our simplification. We can see that there is only small differences noticeable on those areas, and on the, okay, a little bit here too, and on the other places they are fit together really well. And again, those small differences can be visual because we took the values of parameters unrealistically high in order to zoom in into this PDF to see it clearly. And in analytically, we received this kind of simple model for our joint noise. And this is from in one dimension. And again, we need this joint noise for many dimensions. Here is a two-dimensional joint probability distribution. And one thing I want to point out that when we have two or more dimensions, then we have to take into account the correlation between noise elements. So this picture, when we look it from upside down, it changes a little bit to the correlation. Here we have zero correlation, and we can see that this PDF is symmetrical for both axes. And here we have non-zero correlation, and we can see it's tilted a bit depending on the sign of the correlation from one side to other side. But still, it looks pretty similar. And again, anybody who has read this thesis has noticed that this derivation of this two-dimensional convolution took about 7 or 8 pages. And this exact probability distribution function is half pages long, so it's not really user-friendly again. So we have to make some approximations. And here is this approximation of two-dimensional probability distribution function of our joint impulsive and Gaussian noise. And of course, this equation is not so easy to understand. That's why I made this picture there. That one thing we approximated, we just are not usually interested these areas far away from origin, so we just cut them off, made our equations more simple, and again we separated this convolution here with the maximum operator here. And as we are actually interested practically in this area between Gaussian noise becoming weaker than impulsive noise, then what happens here far, far away, it's not really important. What this allowed us to make this approximation more simple, and the result can be seen here. Now, next, I'm going to present you all those 3 detectors briefly, and in order to show their performance, I have to choose some kind of characteristics. So I choose these receiver operator characteristics, which shows this correct detection of is the primary user there or is it not, against this probability of false detection. And then we have this linear line here. This accords to the detector when just one guy throws the coin and says yes, no, yes, no. So anything that is under this line is really bad detector, and more closer to this corner we get this rock curve, the more better detector it indicates. So our goal for ideal life is would have something like that, and this one is also practically a really good curve. So on the those detectors with derivatives based on those same noise models I introduced you. And I really briefly stay on the derivation of the first detector, and the last two ones we just show results. So we took the same one-dimensional joint noise model we introduced before, and as is we're dealing with energy detector, it means that those input samples are squared. So this probability distribution function of squared input variable can be seen here. It looks almost the same, but we must notice that this I is already moved there. And from this we obtained this likelihood function and logarithmic likelihood function, and our detector is based on this likelihood ratio. When we basically compared, we have two models. One model is assuming that we don't have primary signal, and another model assumes that we have primary user signal, and we have some set of observations, and then we try to fit this set of observation into both models and see in which model it gives a higher probability that we are dealing with exactly this model. So the same likelihood ratio, when we take logarithm and cancel out those common terms, then we finally obtain this kind of relatively simple equation. And this equation on this block chart looks something like this. This upper hand here is basically a model for a case that we don't have primary user signal in our received waveform, and this lower hand is a model for a case then we have primary user signal also included. And then we basically compare which arm gives the higher value, which is more probable, and based on this difference we compare it against threshold and make our decision. Is it primary user in signal inside received waveform? So for cognitive radio it means that this channel is occupied, that we cannot use it. Or is there no primary user signal? This means the channel is available and we can use it. And here is this same ROC curve for this energy detector. And we are comparing here the three curves. This green one, that can be seen here probably, at least in the first row I hope. It shows this regular energy detector which works under only Gaussian noise. So this old school stuff, we have regular detector, no impulsive noise. The blue one, that is a little bit lower, it means a little bit worse than the first one, is how our robust detector should work theoretically. It's calculated out from those equations I showed you, and it shows it should almost work as well, but here we already have this impulsive noise with probability 10 in power minus 3. And also show that signal to noise ratio is minus 23 decibels. It means that the signal is 200 times weaker than noise. And this is the length of the detector. We need 2080 samples to get this picture. And this limiting takes place at 128 and minus 128. And then we made those computer simulations for the same model and get this red dashed line. And it shows that theoretical blue and this experimental red, they are really close. And actually it shows also that our experimental results are a little bit better than theoretical. So it seems that it works even a bit better than we assumed. But still, those lines fit well together. So the next, we worked out also this robust cyclostationary feature detector. For energy detector, we only needed to know the power of the primary user signal. In this case, when we have more information about some kind of periodicities in the signal, for example, sampling frequency, some kind of carrier frequency, pilot frequency, then we can use this extra knowledge to get better sensitivity. And again, our approach is at first we limit the received noise. This limiting is based on the parameters of noise, and after this limited noise is used to calculate this cyclic spectrum, then we take the module of the cyclic spectrum and compare it against the threshold. And again, we have these two options. We can decide that the primary signal is present or the primary signal is absent. And this decision making algorithm or equation is presented here. And again, this comparison between theoretical cyclostationary detector without impulsive noise, then our theoretical results with impulsive noise, and computer simulation results. And we can see that this computer simulation fell between of those two lines, and again the fit is really good. And also we must note out that this cyclostationary detector is more sensitive. Its ROC curve is much higher. And later I show you all those three curves together so you can compare them. And I kept all the parameters the same for ease of comparison. And the third one, which we worked out, is analog to this matched filter detector. It's for case when we have almost all the knowledge about primary user signal, the structure, the duration, frequencies, and everything else. Only thing we don't know, is it present or not? So we are searching a known person. We know exactly how he looks, but we don't know is it here or not. And here again, we have basically two channels, and we are comparing the output of them. When we have this searched signal present, then this arm gets the larger value at output than this one. We can make one decision, and if there is no signal present, then they switch. Then this has larger value output of this arm than this arm, and we can compare it again against the threshold and get the opposite decision. And here we go again. Theoretical matched filter detector for a case then when we have no impulsive noise, then our theoretical calculations gave us this kind of ROC curve, and finally those computer simulations leaded us results presented here. Again, all the parameters are same, but we can see that sensitivity has already grown in order of magnitude. And I put also these three types of detectors together. So there's theoretical curves for all those three. And as I told you before, when we have this matched filter, it has the best sensitivity. The ROC curve is closest to this ideal. And this cyclostationary feature detector has poorer performance than this matched filter, but it's still better than energy detector, and the energy detector is the worst one, but again, on the other hand, it needs less information. I also would like to say a few words about some problems that arise during this work and that should need some further analyze. There are many young students in this room here. Maybe you'll find something for yourself. One is the most important that we worked out those detectors on assumption that we have some information about noise parameters. And we also estimated that how precisely we must know these noise parameters. But actually we are still lacking the real algorithm that would find the values of those noise parameters. But this work is still should be done. Then when I talked to you about this cyclostationary feature detector, it was based on just one cyclic correlation frequency. Most of the signals have many cyclic frequencies, so these multi-cycle detectors are actually even more sensitive. So this analyze based on multi-cycle detectors should also carried out someday. And one interesting topic that seems also worth for studying is the so-called three-way detectors. As I told you, all our detectors had these two decisions. They can say that yes, the primary signal is present, or no, there is no primary signal. But there is a possibility that if the detector can't decide on given time, then he can also say in the third option that I don't know yet, and for example ask more time to find out which hypothesis is actually true. Those ones are called three-way detectors, and theory says that finally they should get to the right decision. But just it takes more time. And now I would like to summarize the work that was done in those theses. So this first was mostly introductory. We just have to study the regular detectors before we try to improve them. but we also showed that they are usually very sensitive to impulsive noise. Even the few noise impulses can make the energy detector think that primary signal is already present and your internet connection is lost, at least for some time. Then this our new model was introduced for impulsive noise, and also not just for one-dimensional, but for p dimensions. And also this derivation of this joint noise model and its simplification, this is the part I like the most. I had lots of trouble with it before I find out how to do it. Then we derived these maximum likelihood estimators, and we also had lots of trouble with that before we managed to find out how to model this simplification correctly. And of course, 3 detectors were introduced: the robust energy detector, robust feature detector, and at first those algorithms we got, they worked, but they demanded a really high computational power. So I did some optimization to get almost as good results with much less computing. And also this robust matched filter detector was introduced. And finally, we estimated this how precisely we need to know those noise parameters in order to our detectors work properly. And with this one, I would like to finish my speech now and give it over to the head of the committee.
Thank you very much, and we'll continue with the discussion between opponents and you, and I would ask all other persons to not disturb them. Yes, please.
You start, or me?
Okay.
Yes, start.
I had some problem with the very first picture you showed. So if you can bring it up again.
It's very slide number 1 or
Slide number 1, I guess it was. Take the next one. Go for yeah, that. In that you indicate that the cognitive logic is located in the handset. Is that the intention with that picture?
yes, it can be on mobile communication device, or it can be on stationary. It's
Well,
not much different.
when I read your thesis, my interpretation was that it should be located in the base station, because the base station is the one side that decides what channel he allocates to the mobile. So the mobile just say, "Hey, I want to have a channel," and then it's given to him. So.
Yes. I can explain that. Yes, this first, we have only one standard for cognitive radio. It's this International Electric Engineers EAA 802.22 model, and there is actually say that this cognitive sensing is done in base station. But in theory, in future also these mobile devices, they need to also transmit the data. So for that, do it without interfering primary signal, they must also be aware if there is a free channel or not. So this cognitive system can be practically anywhere. Nowadays, there are actually no working cognitive radio networks yet. The first standard says that really that should be inside a base station, but I think that in the future it could be in any device that is capable of transmitting. All the networks are not based on just base station and some mobile users. There are also networks where there are many equal users. So I think that nowadays it's not there, but it should be in one day.
Maybe.
You're working at that.
Up to now, it's been that the base station is in control and of what's happening in the network, and if the base station finds out that there is no available channel, he just said shut up to the terminal.
Yes, it could be that way, but it depends on exactly which kind of network we're having.
Okay.
have to stand. Dear head of commission, dear members of commission, ladies and gentlemen. This was very interesting reading for me, not because of the details on probability or theory of probability. Namely, the processes where 2 plus 2 is 4 with some probability are more interesting often than processes where 2 plus 2 is 4 with probability 1. And here this work was for me interesting just for this reason. Namely, you also consider case where there is possible to make mistakes and there is probability to make or not to make mistake. And this is interesting. How did you solve the problem to minimize failure probability? I did write a classical opinion on 4 pages and I got 4 parts here. The first part is overview of your work. The second part begins with words opponent has following questions, remarks and notices about the dissertation. Third part has introduction. Opponent has following questions for discussion, and then final opinion about the work and the author of expertise of author. I naturally skip the first part because this was good enough overview. I almost skip also the second part, but almost. I have 2 questions. You didn't mention them, those problems here. What do you mean if you write white and Gaussian noise? White Gaussian noise. What is white noise and what is Gaussian noise? What difference?
Actually, Gaussian noise can be white, but it can also not be white.
Really?
White means, can I draw?
Yeah.
I like drawing. And this is frequency from red to purple in the rainbow. And this is noise power. And white means that this noise is uniformly distributed across the whole spectrum. So in each part of spectrum there is equal amount of noise power.
Oh.
Just like a white light has all the other colors.
Thank you. I didn't know this because we in Tartu consider white noise as exactly Gaussian noise with 0 mean. But I got the answer. Thank you. And the second question from this second part is and what does it mean that signal is completely null when it is not null?
It can, for a good example, when it's not known, when we have this alien communication message from green men, then we don't know anything about what should be inside the signal. But that's not the case, of course. If signal is totally known, then, for example, when you have data communication, we know that this, for example, 0, 1 is presented like positive impulse, or 0 is like negative impulse. Then we should actually know this duration of this impulse and which impulse means, and also we should usually there's some standard about how high this impulse should be. We all know this kind of information. If the signal is more complex, then we have more information.
I see.
But
I
still.
see.
when we try to receive exactly some kind of signal. But if it's unknown, then we just know that somebody is transmitting something, but we don't know what is data or voice. We just have to study the signal to make it clear.
Okay, thank you. Other question of part 2 I leave to your individual work. And now the part 3. Opponent has following questions for discussion. Excuse me. It's 14 already. At first, I, as mathematician, don't understand the term cognitive radio. It means like something we have to look for cognition, like some person to find. Yes, but you have in this institute or this house, let's say maybe in faculty, better tradition of terminology. And this is connected with agents. This is the example of proactive agent. Let's see case if there are more than one how to say secondary user. Then they have to listen each other in the same way, and this is pure agent system, nothing cognitive. So there are proactive agents which are connecting with each other, but this is excuse me, this is not maybe discussion, because I am not expert of cognitive radio, and as I understood, this is known term in the whole world, and let it be so. But please, how it looks like. For example, in Estonia, you think that it's possible that there is one licensed user, and there are several non-licensed user pirates who wait for a moment to give signals. This is the first part. And the second part, what's about listener? I listen some signal. This is called primary signal. I'm listener of primary signal. Primary signal stops for 10 minutes, and then I have to listen secondary signal, or practically how it works.
Okay. Yeah, this is a long question. I hope to remember. First, yes, if there are more than one secondary user, there is a risk that they can collide with each other, and it's actually a pretty old problem for internet topology, called this kind of collision detect. There are many computers were connected to one cable. It could happen that the both start to transmit at the same time. So this is known technology. On the other hand, this thesis is about this kind of single sensing algorithm. It means that just one cognitive user is sitting alone and listening what happens. But we have also another PhD student who studies this cooperative cognitive radio network. It means that these cognitive users, they have some small signaling channel. Signaling channel usually don't take much bandwidth, so it can be used. And they working together, they listening together and then sharing information with each other. So in this case, they also could synchronize this channel used by each other. And again, like Mr. Svensson said, that this also can be controlled by base station. There is one master station, and it says that now you can talk, now you can talk.
Okay, I didn't find nothing about this.
I agree, because it wasn't the main
yes,
topic. We focused on just one small part.
So there are examples, but anyway, the secondary user have to be legal users.
Yes, of course.
Oh, naturally, yes. Very, very nice. Next question. You use term robust.
robust.
Let's say. What does it mean?
In our case, it should mean that our detection algorithm should detect correctly this primary wanted signal, and without or it shouldn't be affected if the background noise is Gaussian or is it impulsive, or in ideal case it shouldn't be not considering at all which kind of background noise there is. This means robust.
Okay. From your thesis, I found out that you define this robust, the meaning of robust, only through those two probabilities you showed here. Because I asked this, and also you showed maybe it's in further works it's quite good to work out the quite exact definition, because robust is used in other areas also, and in very strict senses. As next, here you also showed the experimental or simulated curve. What does it mean, simulated? And excuse me, you use also experimental.
Yes, when I used experimental, then I made this how do you call mistake? I used the wrong word. Actually, these all were computer simulations. We don't have any real experimental data. So.
Well,
and computer simulations, we basically built this model of detector, and then we feed it inside of this model our noise generated by our model, and then we see how this detector acted under different parameters of noise.
And which devices, what computer, what?
We used MATLAB software.
MATLAB.
Yes. And I used the whole computer class because it's lots of computing to done.
But what's about field experiments?
We don't have field experiments. This is theoretical work.
Okay, thank you. In summary, I wrote that I recommend the presented by Ivo Müürsepp doctoral dissertation to defense. Thank you.
Thank you.
I hope it's okay if I sit down, because I see that the notes that I made, they are so weak that if I stand up I can barely read them. So let me start by saying that I think this is really good work. I'm quite impressed with the thesis and the sort of the setup of it, that Ivo has really taken a fairly complex problem and has shown a nice holistic treatment of a complex technical problem, defining a problem statement, describing the state of the art, seeing if the models available today, if they are good enough, or if one needs to develop something else, has come up with a new noise model, developed new receiver structures for it, evaluated the performance, but not only the kind of theoretical know-all kind of ideal for an ideal receiver, but also included the practical parameter estimation and sensitivity to estimation errors. So I think it's a really good work in this sense. And also I think the mathematics skills and the command of tools of probability theory and signal manipulation, it's very good. But I would still like to take up a few technical topics. Maybe Ivo can give some additional clarification about the reasoning behind some decisions and some statements that were made here. Starting with the discussion of the noise model, I guess you were making a case for the existing distribution functions or probability density functions describing mixtures of different noises, that they are analytically quite hard to manipulate and not so useful for developing practical algorithms. And I think one of the arguments that I read was that it's increasingly difficult to handle noises that have more noise components that have more than 1 or 2 dimensions, and that's where I got stuck a little bit, because certainly the development of some of the mathematical framework, it was made quite general, handling in general addressing up to some abstract p-dimensional noise signals. But I didn't quite see where these high-dimensional noise components, where they actually utilized in practical receiver design. I got the impression that the practical receivers at the end all fell back to one-dimensional noise signals, just looking at the individual dimensions one at a time. If you could elaborate on that a little bit.
Yes, the place where we needed this multidimensional noise model is for this cyclostationary feature detector. It has another nice name. It's called a spectral correlation analyzer. So when we need to analyze something based on correlation, then we must see how this correlation, then we must maintain it or take into account in our equations. But yes, when we did it, finally we came back that we can still watch it as almost one-dimensional noise, but it was necessary during this process of development, and also it was shown that if we take it into account as the p-dimensional noise, then we get a little bit better results, but it's much more complex to compute it, so we just made things for us a little bit simpler, and we lost a little bit performance for that. That's the reason we work it out.
Okay. Do you have a feel for what sort of receiver structure you would have ended up with if you would have continued working with the traditional contaminated Gaussian noise models, for example, where you have a convolution of the PDFs instead of sort of the max construction? Would it ended up being something similar? Or?
I'm sure it would be something similar. The basic idea is actually really simple. We can go to this slide. You can see the problem is actually there, that this one part of noise is much larger than the other one. It shouldn't be there. So the basic idea is really simple. We just have to cut it off. But the hard question is where we have to cut it off. When we cut it off too high, then still lots of this impulsive noise energy is going into our detector. But if we cut it too low, then we also will cut off this Gaussian noise, and much worse, we can cut off part of the signal. That was actually the main idea of the work. Where to put your scissors, to say simply.
So your construction, where you have the sort of the max of the two PDFs as your mixture PDF, that gives you a well-defined threshold for cutting off. That's the motivation why you use that model.
And it is actually this maximum operation just enables to simplify this model, and it's intuitive in a way. You can see that here this noise impulse is has much higher value than all the other Gaussian noise impulses, so it dominates. There's actually maybe some little Gaussian part, but this is dominating. So we can just throw the Gaussian part away and make our life easier.
Okay.
And in other way, most of the time this impulsive noise has 0 value, so it's much smaller than the Gaussian. That's why we used to make it simpler, not in the first place for getting better this threshold level.
Okay. Actually related to what you just said, that when you, according to some sort of thresholding operation, if you detect that there is a high magnitude sample, you decide that that's impulsive noise and it should be thrown out. Why do we end up with actually a clipping or a saturation operation instead of making it 0? Because to me it seems like if you clip it, then you are artificially creating some sort of a higher tail to the Gaussian distribution that you end up working with in the detection problem.
Yes, I also mentioned this dilemma in the work. we can use clipping, we can also make it 0. In both ways we should have almost the same amount of error because the actual value is somewhere between this maximum and 0. So we can use both ways. Clipping is just because it looks more, how to say, more realistic, or in digital domain we can do both, but in analog domain this clipping is like more natural thing to do.
But then if you, I guess, throwing it away, which amounts to making the sample equal to 0, I guess in that case you could actually just skip that sample. You don't have to leave the 0 there.
Yes, this can be done in some cases, but when we're throwing one sample away and there is also signal present, then we're throwing some part of signal away. And for cyclostationary feature detector it can cause a problem because we have this nice sine wave inside of noise, and we have this few samples of it. So when, for example, this noise impulse happens somewhere here and they throw it all away, then they're missing an important part of signal, and they can change the frequency and spectrum, and we don't detect the signal anymore in the right place.
Yeah.
That's why I had these 3 options to throw away, to make it 0, to make it equal to threshold, and I tried all of them out.
Okay, but I guess the results of comparing those were not included in
They should be there.
They were there. Okay, maybe I
Okay,
understood. Doesn't matter. Okay, and I had also another, maybe it's a fairly detailed question, but about the assumption of the uniform distribution for the impulsive component. Is this actually sort of a good or reasonable assumption for the impulsive component if you take the range for the uniform distribution as being the minimum and maximum value out of the ADC? It feels to me like if you assume that the impulse, the assumption that the impulse in noise distribution is exactly within that range is only if the actual impulsive noise component happens to be exactly within the limits of the dynamic range of the ADC. If it's actually larger, then you get a lot of clipping, and you should get delta components at the edges of the sort of the uniform part. If it's smaller, then it's just occupying a small region of it.
Well, we can actually see, yes, those.
Yeah.
Okay, they don't.
Yeah. I think these are because
they are not caused by
the
they are not
Gaussian
caused by that.
tails. Yeah.
Yes, there is, if the impulse noise is much larger, then we can have those delta impulses. So we hope that our dynamic diapason is large enough for most of the impulses to fit within it.
Okay. Do you have a feel for what would happen with the performance of your algorithms if you would end up with impulsive noise that is clipped by the ADC and your underlying mixture distribution is something different than you assume?
Might be wrong, but it feels that absolutely nothing bad happens because we are cutting away the high impulses anyway. So.
Okay, I mean, it's intuitive. Okay. Maybe one of the areas where I found that in the thesis, to wrap the entire sort of high-level problem statement, to wrap up the entire high-level problem statement, I missed a little bit the discussion how the method that you describe, that you have developed, how they would actually be applied in practice, because this is a fairly clean-cut or also a sterile environment. If you're just looking for the primary and you make certain fairly bold assumptions, for example, for the matched filter detector, and it kind of goes back to the comment that Dr. Niidla made. What does it mean to have full knowledge of the primary signal? It's not, I guess, partially. Can you really assume that you can know the data contents of the primary signal? And another issue is, in order to actually say that you have that you can regenerate the full waveform, you need to have time synchronization and scaling estimation and all that. Is that practical at SINRs of -20 dB and below?
No. I guess to some level it is practical because we don't have to know the contents of the whole TV show. If we know, for example, how synchronization frame for one looks, we can detect this frame. Of course, more information we have, more sensitive our detector becomes. But again, it needs more and more time to detect. When we just have to watch all the TV show to say that the primary is really sending this TV show, it's not really practical.
Sure.
And yes, there is hidden complexities in this third algorithm. We have to know this much about primary user, but it can be done.
And another detail for the energy detector, there is the noise variance estimation problem that you address, but in order to distinguish between the null hypothesis and the present hypothesis, you also are using the estimate of the signal power, of the primary signal power. How would you obtain an estimate of what that primary signal power is in order to build your metrics for the hypothesis test?
This is, as I pointed out, something that has to be done in the future. We're trying to find something, but it's possibly, I assume that it should be this adaptive algorithm. That first we should start with some kind of estimate, and then when we receive this signal, then we must calculate all the time these corrections, and then just keep the adaptively all the time this.
Okay. That's good.
I think this is the way to done it.
Right. One last comment. I think your performance comparisons compared to receiver structures for all these three fundamental structures, the performance comparison to Gaussian noise-oriented designs shows, of course, that the performance is improved significantly. I think this is really nice, really good results, and show good performance sort of usage potential. I haven't really worked in that area at the detailed level myself, but my feeling is that handling sort of detection problems in mixtures of noises, so this clipping operation, it naturally becomes a part of the front end of different receiver structures. And what I missed a little bit was a performance comparison to some receiver structures that would actually incorporate the clipping operation. I mean, maybe I missed something, but it seemed like your comparison was to this baseline Gaussian design and then using the Huber modification where you have a different kind of a distance function. But it intrinsically, it doesn't include clipping in that sense. Are you aware of other existing designs where clipping is included, and do you have a feel for what the performance of your approaches would be compared to these existing receivers?
Of course, when we did this work, we tried to find similar detectors, but it was really hard, and I didn't find much. That's why I used those ones that were as close as possible. I also talked with my supervisor about this problem, and he said that he also had hard time to find anything. That he had seen some theoretical works that says that you should clip, but it never says where should you do it. That's why I used the nearest one that I got my hands on.
Okay. All in all, I think it's really good work. Congratulations.
Can I continue? I have quite a lot of questions, but I had some problems when interpreting the figures. What was the character of the primary signal? I have understood that in most cases it's sine wave, but when you handle it theoretically, you often tend to use Gaussian. For example, in equation 215, on page 24, you had an expression 214 without the primary signal, and then you said when the primary signal is present, you get the other expression down there. I assume that to make that statement, the primary signal must be Gaussian.
Actually, it don't have to be Gaussian. Energy detector doesn't know anything about the shape of signal it detects, and it doesn't care.
But
we're modeling here, yes, we're using it because it's make again mathematics simpler.
This with gamma functions.
It's the result. It's still same. Because this there is this like this. This variance of signal. It's actually it can be same as the signal power. So if it's if signal is modeled as Gaussian, we can use this variance. But if it's some other type, for example, this sinusoidal we used, then we just take its power, and for sinusoidal signal it's squared. If I'm correct.
Can you use other color?
Oh yes, sorry. Blue is the best one usually. Signal power, basically.
Well, if you say so, but to me it's not obvious that you can make that generalization, but
it works that way.
Okay. Just to show that I read this, so I point out that in equation 217 there is a sign error, or otherwise there's something I don't understand.
That's correct.
Okay.
It took me a few minutes, but then I see it.
Your noise model, it's very nice and very appealing, but I have one problem with it. In reality we know that noise occurs in bursts, and you have not mentioned that at all. So please comment what impact that would have.
Actually, again, I haven't done any close study on that, but if using this clipping, then it's no matter if those noise pulses are far away from each other or if they are close to each other, they all still cut away. But here, of course, if you have many noise pulses, then we probably may have some false detections here, because we have these many maximum value, many samples with this maximum value, so probably this estimator would be a bit higher than average. I guess it would result in a little bit higher false alarm rate.
Yeah, for example, your razor you had on one of the first pictures, it doesn't just send out one impulse, it creates a lot of
again, the other thing is like how short the time we are looking. It also depends on how many impulses are going inside of our window. Probably depends on this also. But yes, I agree that noise usually comes in bursts.
I agree with the other opponents here that the theoretical work you have put in here is very impressive. Especially this which ends in 669, page 69. But I don't see that you use the results anywhere. So my question is just: are you doing this just to motivate that you have to make some simplification in the future to go on?
Well, it was really important because if I don't know how the thing really looks, then I can't know what I should throw away or what I should approximate with what. So I really needed to do this in order to see maybe this two-dimensional model is good enough in the original shape, but it came out that it's not, it's too complex. And so I have to throw away some components. At first I throw away the wrong ones, and I didn't manage to go on many months before I understand what was the mistake. And then I throw away the right ones and everything worked well. So it was necessary for the future work.
Okay. Yeah. On page 70, equation 3.3.30 and 3.3.31. It's very intuitive that 3.31 will be the result when you have the signal in 3.3.30, but it's doesn't it need to be proven if you're mathematically correct?
About that this next equation, this 3.331 came from this previous one. Yes, I must agree that there is mathematical proof.
There's a gap, I guess.
Yes. I must agree, but
have you done the exercise, or do you just assume that this must be valid?
Just assumed it seemed so logical.
It seemed logical.
But
Yeah.
I agree that there should be mathematical proof here.
You have your maximum likelihood estimator here. You describe estimators for sigma and the covariance matrix, and also the probability of impulses. But you do not mention the parameter b at all.
Oh.
Isn't that you have to have some knowledge of that also?
We assumed that this B is fixed to the receiver architecture, for example, which kind of analog to digital converter we are using, or how large is our dynamic diapason. So we assumed in this work that we have knowledge of this B. For example, when the largest...
Is that what you're saying is that you know that if there are impulses, they are always distributed evenly within the full dynamic range?
Yes, this is the assumption we made by this noise model.
But I think that the most severe case for your robust detectors is when you have a B that is much smaller. Because then it's much harder to distinguish between the impulses and the Gaussian noise.
Yes, of course. If we have this poor receiver, which dynamical diapason is too small, then I don't know what happens to this algorithm.
But think about it. Take your razor and go away some meters. Then you have exactly that situation. That your dynamic range is decreasing.
Yes, of course. Those are the problems with real practical use. But this was theoretical work, so we assumed again that we have this proper receiver, and most of the signal is usually falling inside this dynamical diapason. And as we have built this receiver and we have it, so we know the maximum and minimum values the output signal can have. This was our assumption.
Yeah, but can have is not the same as have.
Again, yes, if this actual signal is larger than our diapason, then happens something like we just described here before. That probably these noise impulses will be larger, and they also will be clipped before our algorithm. But we want to get rid of them anyway, so until we're just clipping away those impulse noises, then it's everything okay. It's something like this is like B and minus B, and if happens that this noise is something like that, then at first we cut it off from here, and then later came in our algorithm when we have this decision threshold, and then it cut out from here also. Actually, in this part it doesn't matter is it larger than B or is it not. But of course, if the dynamics is so poor that our signal also comes over here, then we have a problem. Then we need better device.
But what my point is, when you have a very, very large B, which you have in your calculation, there is very few pulses that came close to the Gaussian curve. Most of them came far away outside, and when you have your boundaries, and if it falls outside, you just throw away these samples.
Yes.
So it's easier if B is large. It's much easier than if B is small. So if you have small impulses, the detector has more trouble to work than with large impulses.
If the impulses are really small, then actually we can't make different if they are Gaussian or impulsive. Then they fell inside a Gaussian noise.
Yeah, but I mean, if you have, if B is, for example, 4 sigma, 5 sigma, that order, I get that could be a tricky situation.
It's 4 and 5 sigma is all. It's actually something like on this picture, for example. The sigma is 1. So this is like a 3 sigma. The probability to cross this line is 1 to 1,000, approximately. And yes, if we can keep our signal between those limits, then we can make this be
but
pretty
then
small.
I mean, in that case, the value of B is very essential that you can.
Of course, yes, of course. If it's changing dynamically, then we of course.
Yeah.
On one hand, we have to know it. For example, if it's changing it for ourselves, then actually we should know which value it has.
Yeah.
Again, or if it changes automatically, then we still have to estimate it.
My point is, if you try to make an adaptive system,
Yes,
you should also try to adapt on the B level.
I can agree totally.
Let's talk about the matched filter, robust detector. You said that the primary signal is known. I just want to know, what do you mean with the signal is known? Normally, when we talk about matched filter, we mean that it's the signal shape that is known, and not if it's then data modulate this shape. So is that what you mean here also?
Yes, I mean that this,
Okay.
for example, pulse shapes are known, or duration, amplitude, and so on. Sometimes some synchronization sequences can be longer and also known.
So that means that you are looking in an interval, time interval between null, between 0 and the baud rate time.
Exactly.
If you would like to increase the number of samples, do you have to? What do you do then? You have to sample tighter.
Yes, one option is to sample tighter, and the other one is just take a longer time.
If you sample tighter, what happens with the assumption that the noise is uncorrelated?
If it's really uncorrelated, then nothing happens. But if it has some correlation in it, then it comes out from height. If I sample too quickly, then these noise samples become correlated in real life. Depends how large is this correlation time.
Let's say this is applied to the 3G system. How would that look like?
This detector. Or
Well, you say the signal is known, but what is known in that case?
in 3G signal, we have these spreading codes. This could be one. But the spreading codes, they are different, and they're usually using cold codes or something with low cross correlation. So then we probably.
What I mean is you have to multiply this figure with all the
codes.
codes you have. So
Or just use the one code element.
yeah.
It would be wiser, I guess. Of course, sensitivity is lower again.
But then you have to have then you've got other problems.
Yes. But for example, in this case, we should use maybe this cyclostationary feature detector. It doesn't care much which kind of code there is, but only the coding rate, how fast its symbols are changing. It searches this primary signal to this information.
My interpretation of this particular configuration is that it's of interest for finding the theoretical limit of what you can do, but it really doesn't have any practical use.
I wouldn't agree so much. It's maybe hard to implement, but it can be done at least on some level.
Since the pulse shape is certainly known, all the possible pulse shapes, and also the synchronization is not the problem, but the exact timing it's hard to impossible to obtain.
Typically, the matched filter timing is not a problem, but just here in this model we need exact timing. I can agree.
Excuse me, what does it mean, timing?
So when we must do
Sorry.
subtract this signal from the received waveform, then we must know exact moment when we should start this subtracting, or else we are shifting, we are subtracting from the
Thank you.
delayed version.
Thank you, excuse me.
Yes, this case I must agree.
Yeah, go ahead.
Also, if you need to acquire timing and do synchronization, then actually I think usually in the synchronization process itself you already get performance metrics that tell you whether you have achieved synchronization or not, or with what kind of quality. So maybe it's actually easier to use these metrics than as some sort of characterization whether the signal is there or not.
And anyway, if you want to know if signal is there or not, and we already achieved synchronization, it means that it's there.
Right. Yeah.
We have already
but then,
detected.
maybe it's not necessary to use this.
On the other hand, the cyclostationary receiver that you need to know about the
some periodical information.
some periodically, and in real life that should be quite feasible. You do seem to be a little bit hesitating about that in the thesis. That you might not have this information, but I guess that
That is, yes, usually should be known. Again, it depends on which kind of channels we are observing, so we should know which kind of communication system is working there, and these parameters should be easily available.
But what I mean is if you are a 3G operator, you look in 3G frequency spaces, and in these spaces you should have that kind of information.
Yes. There actually is two opportunities. This cyclostationary feature detector, the cyclic spectrum, is actually a kind of plane. Here we have frequency, we have the cyclic frequency, and when we are searching for some known signal, then we know that it's situated here, for example. And then we just looking this area. This means this actually this single cycle detector. But if we don't know what is there, then we can scan this whole area, and if we find here something, then we can decide that if there is something and there is something, probably that somebody is in the air. We even don't have to know who it is or which kind of signal it's sending. But it needs much more computations. So it's more feasible if you already know where to look those parameters. Just tune us here.
Mm-hmm.
But if you don't know anything, it's unknown signal, then we can check this whole plane and find those peaks. There was also one drawing in the work about this. It was this 4 frequency shift keying modulation example. See, there was lots of those peaks actually. So we can just use one peak, many known peaks, or just search on this plane for unknown peaks. but when we calculate it plane, it takes lots of time.
But computation power, it will come with time. So if it's problem now, it will not be in 10 years or whatever.
Yes, I hope so.
To my view, this is cyclostationary receiver seems quite appealing. The match filter should of course be even better, but I don't think it will work in practice. So I think I will stop there. It has been a pleasure to read to read it, and I think it's very good work. Sorry. No, thank you.
So that's all from opponents, yeah?
I also would like to say it's very good theoretical work. I forgot about this.
So that's all, yeah? You can continue with questions from the members of board. Rein, start from this side.
I should like to thank you for the really theoretical approach to the question, and this is very important, especially for the reason so that software design radio or defined radios, this is a reality today, and there is needed a new approach to solve the radio communication problem. But on the same, I have some questions as well. So first things, as I understood, this is oriented to the cognitive radio network, not to the cognitive radio, because you did not have said no word about what happens then when I start to send or transmit. Then everything changes drastically, and if we have the good algorithm how to start the sending, excellent, but how to finish when I must finish.
You mean that how to detect that the primary user has come back?
No, not primary user. I myself, as the radio owner, I will transmit on the same room, on the same frequency dimensions or everything.
Yes, of course, you can't do the sensing on the same time you're transmitting. It means you are
but then the theory will be, because when I am sending, there is a signal is much stronger than the receiving signal.
Yes, we totally agree. It's the same problem with the radars. Until you're sending your pulse, you can't receive the echoes.
There is so that the radar transmits and then listens.
Yes, but it can't do the both at the same time, because this high power signal leaks to the detector and just blinded or deaf. But it's exactly on the same frequency. In practice, there is two ideas how to do this sensing still while you're transmitting. First, the simplest option is that you send for some small time, and then you just stop and listen again. Is it quiet still? Yes, it is. Then you send again. But it's a problem because you have these gaps inside your information transmission, so you get a lower data rate. So this is one idea proposed called this adaptive frequency hopping. It means that you are sending on one channel and on the same time you're listening the other ones. And then when you want to listen to the same channel you're sending, you just move your transmission to another channel. You have find out that it's unoccupied at the moment, and then you can listen to the same channel, and they are already transmitting on the second one. So you don't need those gaps between transmission. You just have to change the frequency after some time. But this is outside of this thesis of topic.
Yeah, thank you. And another question is especially oriented to the timing. So that this is very important as well to the main user, how long this the signal, what is not his, will last. And the other thing is so that this is the length of the signal you proposed. And the other thing is, how quick is this detector in real time? And what is the computation time?
We calculated this also for this. The energy detector needs the most time, and there was some numbers in this cognitive radio standard. Write it down there. And there they say that in case of signal-to-noise ratio minus 23 decibels, you need to make a decision with those parameters, if I'm correct, and less than 2 seconds was in this standard first. And we calculated in the worst case scenario with those parameters for this energy detector, we needed around a few 100,000 samples to make correction decision. So we have about 200,000 samples in 2 seconds. So we can see that even with very low sampling rate, we can make it within time. But actually, I'm sure the sampling rate is much, much higher. So this developed standard says that there's a, correct this quick listening time, there was around 1 millisecond you made this decision, is it present or not? And then if you're not really sure, then there was this long decision time, it was around 25 milliseconds. So this is the time scale. But this, of course, it's based on this only existing cognitive radio standard. There is not much practical information about it yet, because there is no working cognitive radio networks in present. Maybe some experimental, but not commercial ones.
Thank you. One question is so that you know that nowadays everyday radio there is as well use the signal detectors, and this is called whisch. So that every radio in communication, for example in marine communication, this is listening all the time the situation on this band, and if the signal is higher from some level on this frequency, then it switch on the receiver, and only then. That is for practical reasons. And of course there is a reaction time. There must be some maybe 1/10 of second. Definitely the 2 seconds is too slow, and because the message and the word or sentence in message is maybe itself is 2 seconds. And but how you evaluate this kind of the filter? Is this matched filter or energy detector? The squelch filter.
Squelch filter. It's energy detector.
Yeah, but he knows exactly, but he is listening only this frequency.
But still, it doesn't know which kind of waveform is coming. Are you saying hello
sinusoidal?
Or match filter demands to know the shape of the waveform.
Yeah, okay.
But energy detector needs just only the channel, which one to listen. And it measures if energy level is higher from threshold.
Thank you. I'm sorry for the wasted time.
Yes, I actually agree with honorable colleagues praising your work, and it's theoretically very impressive. Still, I would start with a practical question, pragmatic question, following my neighbors. And have you ever estimated or tried to estimate the necessary computing power that you need to implement your robust detectors?
Yes, there actually should be some estimations also in thesis. For this robust energy detector, when we have n samples, then we have to do also the n squaring operations. Basically n multiplications and also n minus 1 addings, but we can use this moving average filter, so actually we need only two addings per one decision. So this For energy detector, this complexity should be in order of n, if I'm correct.
Okay.
You have to do n competitions to get one decision. Around n, of course, a little bit more. But in cyclostationary, there we are calculating the Fourier transform, and then we're doing also this correlation, and it needs lots of computing.
Yeah.
Even this really small, pretty small number of n causes my computer to do it sometimes a few minutes.
Yeah.
So that's why I told this the computational complexity problem, but we can cut it down, as I told, if it's just looking for just one frequency pair. So then we don't have to compute all the plane, but only the few points there. And matched filter detector again. We are again doing 2 times n squaring here. Also we have to do the n addings. And again it's around linear. Let's say.
Yeah.
Dependence at linear. Yes.
Okay. It was just a curiosity. Now, my question is about approximation of PDF. You probably don't know the precise PDFs, and when you add or multiply or whatever you do, find the convolution of 2 PDFs, then you approximate it, as you said. Do you approximate it as an engineer or as a mathematician? But as an engineer, I mean you just draw the wanted joint PDF, approximate joint PDF.
Say that, as Mr. Svensson pointed out, that I missed this mathematical link between these two parts, then maybe I should say I made it like an engineer.
Okay. The trick is that if you do it like a mathematician, then you find out that approximate PDF quite often doesn't satisfy all the requirements of a probability density in all the working area. And you should be very careful. If you do as an engineer, you might become to have to operate with negative probabilities.
I try to be correct, so that's why this correction factor, that we need to multiply all the distribution function with it to guarantee that the area under this function is 1. And also it doesn't go somewhere negative.
So you can have the area 1 even though although you have in some places negative probability, which is difficult to implement.
At least we didn't notice it during the work. I'm not a mathematician, but I tried to be as correct as I could.
Then to the very end you give promises for the future. And it's a really interesting problem if you go to recursive noise parameter estimation. Do you have any particular ideas how you would do that? Do you intend to use Bayesian estimation or any other?
Must be honest that I haven't think so detailedly how should be done. I have this general idea that we should try this adaptive algorithm and hope it will converge into result that we are needing, but I am afraid that there should be lots of troubles to doing that. But if we succeed it, then this theory may turn into practice one day. So it is interesting problem.
Okay. We could carry on, but thank you very much.
Okay, well, I have got already several answers to my early questions, thanks to my colleagues. The only thing I missed actually, that's maybe clear statement what is new or what is a state of the art and where is the edge, what you have shifted forward in your thesis. I agree that it's theoretically a very tough approach, and of course there is something what you can do better in approaching to the practical problems and assumptions. But if you can characterize shortly what is actually the leading edge and how you shifted it forward in your work.
As I said before, to take it very compactly, then this shifting edges that we probably knew before that this clipping is answer for this impulsive noise problem, but now we have spotted out the exact spot that we should clip here. I think this is the little movement of the edge of human knowledge.
Okay. Well, the other question is also related to future work. It seems, well, in your detectors, you basically have sort of reactive decision making, which means that you observe the signals and detect something, and then you make decision how to proceed. You switch to the other frequency or choose what kind of frequency to choose there. If you want to be proactive, as it was mentioned here, then probably you should somehow predict what could be the free frequency where to hop after your decision, and then you have to take into account your past, somehow learn from the past events, and then make some predictions or hypotheses what could be the best option for the future hop. Have you considered this, or how you could fit your results into this idea?
No, I must be honest that I haven't considered that much. But about this a priori information, it's not really hard sometimes to get. For example, when we have cognitive radio network working on this TV channel frequencies, we can just take a TV guide and we already have the a priori information from which channel, which time the signal is coming or which not. And this is actually, it's not a joke, but it's a thing that's really considered. We can have some databases about when these primary transmitters are available, and we can get some of our information from the other way. We don't have to use the detectors only when we're moving up to this cognitive network. But this is, again, falls a bit outside of this work.
Can I ask an additional question? It's about the applications. You have several times mentioned the application of TV channels and other similar stationary things. Can you foresee any less determined applications for cognitive radio, like ad hoc networks?
Yes,
which are not based on regularly established infrastructure or networks, or which actually networks are dynamically created, and they nevertheless they want to exchange or communicate there by cognitive type of radios.
Yes, when I was talking about this TV spectrum, that's again because this first existing standard is built for using this TV spectrum for this rural area network connection, which is giving the internet for these single houses inside of thick forest. And that's why this TV example so often. And yes, this television is the primary user, and yes, if cognitive system is in somewhere in this coverage area of this TV station, then of course these ad hoc networks can be built. If all these cognitive users are sensing that TV is already switched off or it's so far away, its signal is it's smaller than this is according to standard, then they can build up whatever kind of network they are capable of doing there. So usually I don't think there's going to be some cognitive television transmitters. It's more like pirate TV then.
Okay, thank you. Yes. First, as a comment again. This theoretical part is very impressive, and especially these long analytical formulas, I should say analog formulas for people like me. But to ask a question, if you talk about this most simple detectors, you are using some root mean square or some squaring, talking energy, again squaring. But as much as I remember from older times, if somebody says detector in radio, this could also mean some peak or amplitude detector or peak to peak. This could be rectifying and averaging, or in other words, taking absolute value and averaging, which could be done synchronously or non-synchronously, and so on, from one side or from other side. From practical viewpoint, not theoretical, but practical viewpoint, this root mean squares and such kind of things are not very convenient to implement in real life. Maybe there are some other approximations by using of this peak or amplitude or averaging or some other statistical moments than root mean square, for example. And what happens if we have any idea, other statistical moments instead of?
Try to compare this energy detector with some other similar detector. Actually, this one is this absolute value detector, for example. But this square detector is probably best for this energy detector. On one hand, it's really sensitive, and on the other hand, it's not really complex. And as much as I know, it's practically most widely used one. And I don't agree that it's hard to implement. You can make a square detector by a simple diode in analog technology, but in digital technology, of course, squaring is again not a problem at all. It's just simply multiplication operations, and we have really fast signal processors already. So implementing is relatively easy.
Okay, thank you.
Thank you. Unfortunately, my colleagues have discussed my not stupid questions. I have never stupid questions. These primitive questions, maybe. It has been a long time when sharing in space and time have been used in memories, time sharing, and so on. Why this? Is it correct if I call it cognitive radio is frequency sharing?
It could be both. It could. You can share the frequencies, but you can share the available time in one frequency also.
Yeah, but cognitive radio adds frequency sharing. Is it correct?
It's the basic idea.
Yeah, is it so? Why it happened so late? 1998. Why not before?
First, to get to the idea of this cognitive radio, we needed this software-defined radio first, because cognitive radio is like a step forward for this. And of course, one hand is this growth of computational power. Now we have enough computing power to do such tricky things. And probably the another thing that this wireless internet has already also started to grow about those times, because this is the most demanding application that needs most of this bandwidth and frequency. There wasn't much trouble to share the spectrum between TV stations or radio stations. But now we have more and more users. They are moving all around everywhere, and they want more and more faster internet in their cell phone. It's probably those reasons together.
There was enough frequency space, so-called, yeah?
Yes, but there is lots of frequency space, but it's licensed. It belongs to somebody, and everybody else are forbidden to use it.
And about time slots, you will use anyway your transmitter during some time slot. Is it 2 seconds or different, or how is determined?
I mean, like how
you detect that this band is available.
Mm-hmm. Oh, yes,
Which
and
is
how long
time
you should
slot
transmit?
You can use it.
This is a really good question.
Of course, absolutely.
I'm really sure that it's. I haven't considered it much, but there's if you send too little time, then this secondary user will have this small bandwidth. If you send too long time before listening again, then there is danger that you're interfering with primary user. So it's lots of probability theory will be there when you start to analyze this. I haven't done it, but it's hard to find this optimal time. I guess it actually depends again in which kind of frequency we are working, which is the nature of this primary user. For example, when we're working again on this TV network, there is two possible states that this TV transmitter is sending for a long time. They usually don't make films in 5 minutes. And if it's switched off, then it's probably going to be for a long time. But then again, when we want to work for example, this 3G or 4G mobile network, then those so-called phone calls are often really short terms, and they may be initiated at any moment. So then we probably should have this shorter period when between sending and listening again. So it's a complex problem, but
is there any agreements about time slots? You know, page sizes in memory, for example, or
yes,
bits
again,
per
there
package?
probably is, but I haven't
fixed?
No? Memorized this. No. I can't answer that.
Okay. Do you or cognitive radio is using polling? You know, there are several bands, you know, and you detect all them at the same time or polling them in some sequence, or how it's...
It depends on detector again. When you use the energy detector or this match filter, then you must check the channel by channel. But for if you're using this cyclostationary feature detector, it calculates the Fourier transformation anyway, so you can at the same time simultaneously scan the larger area, some whole bandwidth.
Many bands in the same time.
But again,
then they choose some of them, yeah?
But it needs more computational power again. So you can do it both ways, depends on which detector you're using.
Mm-hmm. But energy detector, you target only one band, yeah?
Yes, because it
and then another band.
If you would take a wide bandwidth, then you only know that somewhere in this bandwidth there is primary, but you don't know in which frequency is available and which one is not. So that's why you must do the narrow channels.
Yeah, if something is not available, you go to the next one and so on, yeah? And is the energy detector faster, much faster?
Energy detector,
so cyclostationary?
No, it's actually the slowest of them all. No, it's not slower than... yes, it's the slowest, because it needs the longest realization to get the same performance.
Why to use it?
It's the simplest.
And
it leads the smallest amount a priori information.
Less money.
Yes, less money.
But worse.
Just like everything, Mother Nature likes to play with us.
Okay, I don't know.
To get something from here, then you have
more questions from the members of board? Yeah.
Just to follow up your comment that energy detector is sort of the simplest and in some sense most universally usable. I just wanted to just look at the figure that you also had, the performance of the performance comparison of the detectors. Actually, doesn't it look like the energy detector receive operating curve is pretty much equal to this coin flipping?
Yes,
so, I mean, is it really useful in practice?
It's because of this, it's really close to the signal to noise ratio wall in this case.
Okay.
But if the signal to noise ratio is better, then it works really well.
Okay, so you have chosen that operating point to have a fair comparison.
Exactly.
But in practice, you would use more
also
samples.
because of this side, of this number from the standard. Okay. And again, if I make this signal to noise ratio much better, then this would work too well again for this picture. So it's hard to put the three of them together in one picture.
Okay.
More questions? Oh, okay, sorry.
On page 30, you introduced something you call signal-to-noise ratio wall, and to make requirements on the accuracy of the sigma you need to have. Then on chapter 7, you have a very good analysis of the requirement on the sigma, but you never comment on these walls. Why is that?
Comment. I don't understand exactly the question.
Well, you say here that you have a scenario wall that you need a certain accuracy on calculation of sigma. And then you you do this exercise. You look on how accurate must your sigma was, but you never comment this on this wall statement you have here.
Okay. Yes. I must agree.
You say we have this requirement of minus 21 dB in SNR, so that in itself puts some requirement in us as on the sigma, and you analyze it for the different, but you never comment. Do we meet or do we not meet this requirement?
Okay. Yes, I agree that I should put this same SNR wall thing also to the 7th chapter. But in the 7th chapter it can be seen that this wall thing is a property of the energy detector in general. It's not getting much better or much worse when we use the robust detector. Just a basic property of this energy detection method when we use this average square, mean square detection. So lower is the signal to noise ratio, then more accurately we must know exact value of the noise power.
That seems to be all from audience. Or somebody wants to ask? No, nobody. Thank you very much. Now it's your last word as non-doctor.
Uh-huh. Haven't prepared much for that. Okay, I would like to thank everybody for coming this 2-hour show. I hope it was interesting. I'm really grateful to opponents that they read my thesis really carefully. They found all the small details I've done wrong, and I really appreciate that you had time to come here for me. Of course, thanking the committee, and especially I want to thank the professor Tõnu Trump. Without him, I wouldn't be here. He took me and made me do the work half day when I wasn't in the Facebook. And I'm really grateful, and next to him is sitting the guy who's probably defending here in a year or two. And of course I'm thanking all my colleagues for any kind of advice and help, and all my friends who listen to this endless complaining of mine over the years. And really nice that I see also many of my students here. I hope I can be in this room listening your master's defense and maybe some of PhD defense in a few years. And of course, thank you everybody else I forgot to mention. And I would like to especially thank my father, who's sitting there in the corner. If there wouldn't be Professor Trump, I wouldn't be here, but if it wouldn't be my father, then I probably wouldn't be here in the area at all. And it's been already 2 hours, so I wouldn't make it any longer. Thank you, everybody.